everybody. Welcome again. I'm Josie, and today I'm going to be talking to you about the mid-rise world. About 4 to 6 stories is kind of where we found our niche, and I'm going to focus on multi-unit residential buildings, and within those, all the lessons we've learned, because that seems to be the only thing that I like to talk about in these discussions. So from detailing all the way to constructability and what we've learned along the way. So as I mentioned, I'm from Schilthuis Construction. We've been a company for about 68 years. I haven't been there for 68 years, but it's been around. We specialize in industrial, commercial, and multi-residential buildings. We do anything from construction management to design build and much more. We did 2016 was our first passive house experience. That's when we also got our training, and ever since then we've been kind of on board with all things passive house, both PHIUS and PHI. We now have multiple superintendents and project managers and laborers that are now trained by the Institute or by ourselves in passive house construction, and we have many sub-trades that are also well on board. Currently we've completed 10 multi-unit residential passive house buildings, a mixture of some that are fully certified and some that aren't. And by the end of 2024, we hope to have 15 completed if everything goes well with schedule. And in 2025, hopefully more to come. These are a few that I'd just like to show you. In the top left corner is actually, we had boots on the ground there, what did we say, 4 years ago. We call it Parkdale Landing or Melvin. And in the middle, we have a building that we call Parkdale Phase 2 with Indwell Community Homes. On the far right, we are doing a project with City Housing Hamilton that is going to be PHI certified. The bottom left is the YWCA in Hamilton, which I think should be PHI certified. In the middle is one we like to call Lakeshore Lofts. Down the bottom is Houston Street Baptist Church, or I think they call it James Street Baptist Church now. It was a church and Indwell Community Homes combo. So church and affordable housing, which is certified. And then on the far right, we have a renovation project actually that is called Dogwood Suites with Indwell. So we do a lot of passive house buildings for affordable housing, which seems to be the route that Hamilton is going, which is great because we love to work with them. So the typical planning process that we all see is you go from concept design to build. But when we're working with low-income multi-unit residential buildings, we like to break it down a little bit differently or in more steps. And we like to look at the constructability, the cost optimization, and the performance of all of our details. What I'd like to start with, of course, is our famous air barrier, our thing that we all talk about, the air boss that is in charge of this, and our lifeline basically to our passive house buildings. So we've done a few different substrates for our passive house buildings, one being precast. So I want to, in the next few slides, break down each of these categories, what worked for us constructability-wise, the cost optimization of it, and then the performance. So for total precast, because of the way it's constructed and the finished exterior that we had on this building, all of our air barrier had to be on the inside. So we had to find a way to seal that continuously from the interior, which is not normally what we are used to. With that also, due to fully grouting the ends of our hollow core slabs, we could not tape past the floor level, which means that floor to floor, nothing could be continuous. So we had to come up with a different way to do that. What we ended up doing is, of course, in the far left picture there, you can see that we taped all the vertical joints. We also taped from the wall to the ceiling, and we taped from the floor to the wall. So we kind of created some sort of air tightness barrier in there, and with the hollow core completely grouted solid on the ends, this was the best way we could get our air tightness. We also then had panel connections, and this one they were bolted, and we had to also tape over those. We also filled them in with insulation, as these were sandwich panels, so we wanted to make the insulation as continuous as possible. And for a final number on this building, we ended up reaching 0.37 air changes per hour at 50 pascals. So it turned out to be a pretty successful air tightness test there. In terms of cost optimization, this compared to fully sealing the exterior of the building ended up being fairly cost effective. as we're doing only vertical and horizontal joints, because the rest of the sandwich panel was then acting as our air barrier. This is our air barrier that we usually use on either stick framed or a hybrid between precast and stick framed. And it's the peel and stick barrier that everybody likes to use. So we've used a few different ones. These are just 2 examples with a Henry Blueskin and the 3M product. One has a primer, one doesn't have a primer. In terms of use, we found that it's all been about the installer. For constructability, both are easy enough to use. For performance, they're great because they're self-sealing, which we found is a great tool, versus something if you're using, say, a zip board, that you have to be a little bit more careful when you're doing your penetrations on the outside or your screws for your cladding. So we've really enjoyed using these products. For cost optimization, it all comes down to really for us the install and how fast and effective we can install it. So again, they're pretty on the same level in that sense. And performance-wise, with this one we got 0.33 air changes per hour at 50 pascals. Again, this is just an average of a few buildings that we've used with this air tightness barrier method. So now I want to move on to cladding. So I call this stick built because this is normally what we use only when we're doing fully wood construction. This is when we step into the combustible world and not into the non-combustible world. So this is a strategy that we use the long screw method with. We did 3 inches of exterior insulation because we had the opportunity to do 5.5 inches of insulation on the interior studs. And then we did horizontal and vertical strapping with the long screw method to hold on our insulation here. And then in turn, this is how our cladding would be attached to our building. For constructability, this was fairly easy for us to install once we had to get the long screw method engineered. Performance-wise, it, as far as we know, performed well. We got good air tightness testing here. And for cost optimization, this as well was very cost effective for us as we were stick framing the building. So we already had the crews there that were doing wood framing. Then we have what I like to call like a hybrid cladding insulation. This is for buildings. Sometimes we use a combination of steel studs, or we're doing wood studs, or hollow core floors, or stick built. We can do all sorts of building constructions with this method. And this is the one I'm focusing on because there's millions of cladding, and we all know the fiberglass clips that are available to us. But I wanted to focus a little bit on doing brick. So this is kind of how we've done our brick shelf angles, which has been a large topic since we started this process, as our very first project had brick on it and we had no idea how to make this thermally broken. So the detail there shows that we have a cast-in shear stud fin into our floor level, which would be our, at this point it was our hollow core, or it would be solid for that core. And then we had a fin coming out, and in between that fin and our exterior shelf angle, we had a thermal break. So I actually have a pointer. There is a thermal break right here in between this bolt. So this is the fin that is connected to our shear studs coming through, and this is the fin that is connected to our shelf angle on the outside, and there is a small 1-inch thermal break fiberglass piece in between. So this is how we thermally broke our shelf angles, and we did this per floor. So this ended up being fairly cost effective versus another method that we had, which I'll show on the next slides. And in terms of performance, we found through thermal imaging that it was fairly well performing, and cost optimization and constructability go hand in hand, as we only had to do one of these per floor instead of doing a bunch. Again, I'll show you the next slide, a bunch of different supports for our shelf angle. And they were cast in, so it became easier for us to just go and install these. The only thing that came a little bit pricey was having the thermal breaks in between each of these supports. But again, you'll see what our alternative was. We have in the past used things called ferro brackets, which for our project, they were very time consuming, and it could have been just because of the design. And the ferro bracket is this piece right here holding your shelf angle. And we had these at I believe every floor level as well, but depending on how high your brick goes, you might need them more periodically. And the time-consuming part of this was that we had to fill each one of these with insulation all the way up the building, which obviously adds cost and time. Performance-wise, they ended up doing okay, but this was also another thing that we had to do. So behind each clip, we had to put a thermal break, right? You can see, I don't know if this was the load, if this was the bottom, or why we had so many clips so close together. That could be a miss on our end, but you could imagine that this is going to add up very, very fast and take a long time to install. And there were points where, due to different projections, where if it was at floor level or if it was at, say, the middle of the, in between the middle of the floors, we had to cut out dense glass in parts to put our thermal break in there just to make it flush and continuous all the way down. So we have explored different details with supporting brick in a passive house, and we're pretty happy with where we are now, but we're always open to different solutions. Now, windows is always something that we like to discuss. So right now, we are kind of stuck on the window buck, which is a 3/4 inch plywood buck that we like to use. This is typically only for buildings that we're using wood framing on the outside, whether it be structural or just infill. We're using it during our wood framed buildings. So in these bucks, we have many different ways of sealing them. We've sealed with a paint-on liquid vapor barrier. We've done like a blueskin with tape. We've done 3M with tape. We've now, ever since our first building, switched from sealing it on the outside to sealing it on the inside now. So that's just become a common practice. One of the performance or constructability problems we have had is not necessarily with the product of the paint-on vapor barrier, but sometimes in the imperfections in our plywood buck. There is a different barrier that you have to put in larger gaps, and sometimes we've found that we've had actual imperfections in the buck itself, so in the plywood, and when there are imperfections in that plywood and it opens a gap that we haven't put the extra, like I think the masticky stuff that can bridge gaps, we've had air leakage actually through the buck itself. So we've then just gone back to using a membrane for the time being, just to avoid any issues that we've had in the past. But for cost, I mean, they all end up taking similar amounts of labor on our end. The paint-on was actually a little bit beneficial for timing, because as these bucks were built prior to coming to site, they could have been painted prior to coming to site as well. So that was a useful thing in terms of constructability, but in the end, we've just switched back to doing peel and stick. This is something that we do when we're using, say, steel studs on the exterior. We're not necessarily going to do a wood buck. I'm not a code expert, but I'm pretty sure if we're going to stay non-combustible, we're going to stay non-combustible throughout the whole exterior of our building. So we've used fiberglass angles. This was one of our first buildings where we did the fiberglass angle on top of our exterior barrier, but I think now we have started wrapping our blueskin all the way into our opening. But the message here is that we've used fiberglass angles a lot on supporting our exterior doors outbound of the structure, and because we can get them in bulk and we can sometimes get them pre-cut, they have been fairly cost-effective for us. Not as cost-effective as the buck will be, but in these situations where we're using exterior steel studs, we're not going to be using wood bucks. It's just going to take too much time, and I believe we are not allowed to do that. And performance-wise, yes, these are also great. Wanted to touch on a few structural thermal breaks. We've done structural thermal breaks that are holding up entire 5 stories of the building. We've done structural thermal breaks that are holding up a large parapet with steel posts in it, and then structural thermal breaks that are going to be just on like a roof railing. The thing that we've found here is that obviously the thinner, the cheaper they end up being. The constructability aspect that we like about them is you can get them pre-drilled a lot. So they come already pre-drilled. You just slap these things under, whether it be a roof anchor, a railing, or whatever it is, and you screw them right down and you're good to go. So we've really enjoyed that. Performance-wise, they, depending on their R value, they all end up being fairly similar for what they are. One thing that we have experienced is if you get, say, a structural insulation that isn't as strong as, say, one of these fiberglass pieces, we've had some of our doors have problems sinking because, yes, they can handle the load, but at different times when the door is open, or it has loading on different parts of that door frame. So we've had them sinking and have to be readjusted a lot. So we've now forgotten to go to the structural insulation. We're just going to do a fiberglass angle underneath those door frames now and not worry about the different loading. This is just one I wanted to mention because I want to get back to it, but I haven't seemed to found the right project for it, is doing a raft slab. I know that cost-wise, sometimes it can come in a little bit higher because there's lots of form work all the way around the slab, depending on the size of your building. There's also a lot of reinforcing in it. But in terms of under-slab work, it is a dream. We'll just do our compaction, and then we have, at our raft thickening, we have our under-slab vapor barrier, and then we put our insulation. And then we pour our thickening, and what we do in the meantime, we bring it up, tape it, insulate around it, and then we get ready for the rest of our slab to pour. And once our vapor barrier on the rest of the building is laid out, we unfold it, connect it all, and we are good to go. So this is a really nice detail that I want to get back to doing. It can be a little bit more costly, but with the right project and the right needs. So if you have height restrictions, it is good to do a raft slab foundation, and if you have to spread more of your load a little bit wider, this is also a good option. So I'm really just trying to push raft slab foundations for projects because they're a dream for us to work with. Ceiling, of course, we all know where we've come with ceiling since we've started our passive house journeys. It used to be all these special ways to tape, but now we've started finding all these fancy products that you can do, whether they're gaskets or whether they're homemade. We use EPDM sheets. We just get a bunch of them from roofers, and we cut them up nice and tight, slide it over, and then do like an extra little taping detail just to ensure that it's tight. Even though you can see if I'm up here, it's pretty tight, but we're never too sure. So they've gotten a lot cleaner. But this is the detail I'm most excited about talking about today. Is something that I experienced about 2 weeks ago, is how to seal all these pipes that are super close together. So usually what we like to tell our trades is please keep them at least far enough apart that your hand could realistically go in between. Otherwise we can't cut a piece of EPDM to shove them over, or we can't get our hand in there to tape them. This, unfortunately, is a building that is also feeding a phase 2 of the building. We don't have too many options. A lot of these have to come out of the floor and into the underside of the panel. So when we discussed this with them, they said, no chance, we can't separate them. These ones go right into the panel. Other ones, if we had spread these out, the whole floor, we wouldn't have any floor space in this room. So we didn't really have many options. So as you can see, there is just a million pipes here, and they're all smushed, worse than this, smushed right together. So how do we do this? How do we seal our underslab here? So I don't know if anybody knows Zahn Engineering, but we've been working with them on this. What we came up with was we did a little mock-up on site. We had a pipe through. We had our vapor barrier taped to the lower layer of insulation. We did 2 layers of 4-inch. So we taped our vapor barrier to the lower layer of insulation, and then we cut a larger hole in our top layer of insulation, almost forming this hole up like we were about to pour concrete. And we poured a flowable sealant in there. We found this roofing product. It was called Sopramastic. And it's usually for, I think, renovations of roof penetrations. But we liked it because it's a sealant, almost like a caulking, but it's flowable. So you put it in there, and after a few minutes, it'll find any crack it can. And it actually didn't pour out the other side of the insulation. So it wouldn't go into the abyss. It would stay kind of in its form here. So we did that trial, and everybody was happy with it, and away we went. So we did that here. This was our first step. We poured it, and it actually got in between most, if not all, of the pipes there. Hardened up after, I would say, a day or 2. And still had a little bit of bounce to it, so it means that it will stretch. And then to top it off, we spray foamed the rest, because there was no way, if we can't get sealing around there, we can't cut rigid insulation around there. And this is, again, us topping it off with spray foam, and this is our poured concrete floor. Again, lots of electrical pipes. So that was a detail that we were really excited to figure out. Cost-wise, about $100 a bag. We used 14 bags, so it's not cheap. But if you had to think if those penetrations were all separated out and how much work and time it would be to seal all of those, because individually there are many, many penetrations. Hard to do the math, but to me it would almost, with labor rates these days, probably come to similar pricing. So we thought for something that took us maybe a couple hours, pretty happy. So going through constructability, cost optimization, and performance on window details, we talked bucks versus angles. Constructability-wise, depends on what your building is. Cost optimization, bucks end up being cheaper for us because we can pre-make them all and bring them to site. And then performance, it depends on what you use for your barrier. Under slab sealing, we're really happy with the performance of our flowable sealant, or we're hoping to be happy with the performance of our flowable sealant. Constructability, way easier. And then cost optimization, well, it's still up for debate. Thermal breaks, we kind of went through this as well. For constructability, they are fairly simple. No matter what kind of brand you get, they can usually all pre-drill them. They come on site, you put them in. Cost optimization depends on how many you have. If you're doing a detail like we did with the ferro brackets, that's going to be a lot of money. There's a lot of breaks there. If you separate them out a little bit more, like on the other detail we did with the cast-ins, it ended up being a little bit more cost-effective. Performance, also similar. Oops. And then exterior barrier. One thing I forgot to mention when we were talking about them is lifespan. So that's the debate back and forth. Depending on when your sequencing is for your siding, you have to take into account when you're going to be closing that barrier up. So different products have different lifespans out in the environment. So before you close them up, make sure that that is something that you're looking at, because that'll have a huge play on performance. We've accidentally left our exterior air barrier out way past that barrier lifespan. So make sure that you look into that before, because that'll affect your performance. And in summary, of course, we all know that passive house buildings are all about learning and growing. We change our details all the time, and we adapt what has worked and what hasn't. We are still learning, even though we've done it way too many times, but there's always a new perspective, a new detail, and a better way to do it. Something that we like to concentrate on for low to mid-rise multi-unit residential is looking at the tenant use, the cost, the future, and the timeline. These are just a few things that I like to focus on. I can't, of course, talk about all these things today, like tenant use. I could do a whole other talk about that, but the future, the cost, and the timeline all play into constructability, cost optimization, and performance. And then sequencing, of course, is everything. Thank you.